Okay, in this lecture, we're going to talk about dimensional analysis, specifically about the metric system and some metric to English conversions. So let's get started. Dimensional analysis. Now, in any science class, this is sort of a key component and a skill you really want to master, right? It's a problem-solving strategy, and it's used in all scientific mathematical courses and problems. Anything with a unit, which is a measurement, and a conversion is going to have this sort of methodology to it. So let's get some background with dimensional analysis before we jump into actually quantitative problem solving, and just define sort of these conversion factors. Some books call them unit equations, which is going to relate two quantities that are equal. Now, in the previous lecture, we talked about this metric system in a way of relating these two units, right? We talked about 1 kilometer being 1,000 meters, right? Or we talked about 1 megagram being 1,000,000 grams, 10 to the 6 grams. That's a better looking 6, there we go. 1 megagram being 10 to the 6 grams. So these are unit equations, right? And really all a unit equation is relating one unit to another. So the unit equation is an exact relationship with the metric system. As we'll see in the English to metric conversions, that's not necessarily the case. But with regard to metric, which is what we're talking about here, this is a metric unit, this is a metric unit. So in this metric unit equation, this is an exact relationship. So you don't really have to worry about 1 sig fig versus, 1,000,000, 10 to the 6, so 6 or 7 sig figs. You just remember this as a conversion factor. You're using it as part of the problem solving, but it's not itself affecting significant figures. Now, these unit equations are going to appear as these parentheses, these ratios in your problem solving. Okay, so now instead of writing it as an equation with an equal sign, we're writing it as this ratio. And so we're going to call this a unit factor or a unit ratio. That's usually the terminology that we use. Now, using dimensional analysis is about using these unit factors, right, in the right order, having the numerator and the denominator in the right place. And this is the most common part that students will mess up, right? And using this unit factor that is a ratio of these two equivalent quantities, it depends, are you going to write it like this or are you going to write it like this? And we'll describe exactly which way you're going to write it and why. But taking this unit equation and turning it into a unit factor, well, you could have two of them. One where the kilometers in the numerator and one where the kilometers in the denominator. So how are you going to decide which one of these two you're going to use, right? You're converting between meters and kilometers. You know the unit equation. Which unit factor do you use? Here's the answer, okay? Step 1 in any unit conversion is to write that unit on the right size. What are we asked for, okay? So there's going to be, a lot of words in a long problem, and there's going to be somewhere a unit that is asked for. So maybe it'll say like, how many meters, for example. Okay, if that's what's asked for, that goes on the right, and I'm going to write an equal sign and meters and the unit m. Write the given value on the left side. So up here it might say, okay, the length is 54 centimeters. That's the given. So whatever unit is given with a number, that's the given value. That over here on the left. Okay, so that's step 2. Okay, you have to do these two things, and please take the time to write the unit down. Even if you think you know how to do it immediately, skipping to the calculator, trying to do it in your head are recipes for failure. Take the time to write it out. Please, 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 I beg you. So writing it out, 54 centimeters, going to meters. Now we put in the unit factor, okay? And that's where these set of parentheses comes in, right? And the given unit right here is always going to appear in the bottom of this first unit factor. So whatever you write here, this is why it's important to write out the units. Whatever you write here, immediately write it down here. Okay, the given unit should appear on the bottom of this unit factor. Now, there might be multiple unit factors, and we'll get to that, but this is the way to start. What are you asked for? What are you given? Immediately write that given one down here. And now think of the unit factor that's needed to convert centimeters to meters. Centimeters is going to cancel. Meters will go in the top because whatever unit you're asked for, or sorry, whatever unit you're asked for must at some point appear in a numerator. It doesn't have to be this first one. There might be multiple parentheses, but it must appear somewhere in the numerator. Here we can do it in one step, and you'll get some familiarity with when you can do it in one step and when you can't. But now that you have the units spelled out, centimeters is canceled and gone away, you're left with meters. Now you fill in the numbers. What is the unit equation in your head that relates meters to centimeters? Well, maybe you remember 100 centimeters in a meter. Or maybe you remember 1 centimeter is 10 to the negative 2 meters. These two things are equivalent. Doesn't matter which one you memorize and use. What matters is that the number that goes with centimeters winds up next to centimeters in the unit factor. And the number that is next to meters winds up next to meters in the unit factor. And now you multiply across the top, divide by the bottom, and you should get 0.54 meters. Okay, so that should be the answer here. 0.54 centimeters went away, left me with meters. 54 divided by 100 times 1 is 0.54. Just 2 sig figs because these unit factors for metric to metric don't affect sig figs. So there's 2 sig figs here. My final answer should have 2 significant figures, and it does. Okay, so that's one example of this dimensional analysis we're talking about. Let's look at one more. What is the mass in kilograms of a 325 milligram pill? All right, let's use Prof. Melko's patented 3-step methodology here. What is the mass in grams? Equals grams. Of a 325 milligram pill, 325 milligram pill. Writing out my units. We want grams, so we put it on the right. We've written down what's given, 325 milligrams. We apply a unit factor. Okay, so step 3 here is apply this unit factor. We're going to look at what unit is given, milligrams. That must go down here. What unit is asked for, grams. That must go up here. And now I have to apply the unit factor. What is the relationship between milligrams and grams? Maybe I've remembered 1 milligram is 10 to the negative 3 grams. And so I put the 1 with the milligram, right? It's easy because I've written the units where they need to go. Now I simply write next to the unit. What is next to the unit in my identified unit equation, right? That's why it's important to memorize all these relationships we talked about last lecture about 1 milli is 10 to the negative 3. So 1 milligram is 10 to the negative 3 grams. And so you can do this for nanograms or picograms or anything in this table. So 1 milligram is 10 to the negative 3 grams. Multiply across the top, divide by the bottom. Remember, a unit divided by itself goes away. That's the point of dimensional analysis, is we are moving from this unit we're given to this final unit. Milligrams gets canceled out because a unit divided by itself is canceled. And we're left with 325 times 10 to the negative 3. That's going to equal our final answer here of 0.325 grams. Right? We started with 3 sig figs. This doesn't affect sig figs. So we're left with 3 sig figs in our answer 1, 2, 3. Okay, so that shows a very straightforward way to conduct dimensional analysis. Again, the most important part is to write out the units. I can't tell you how many times students will do this. Either try it in their head or write down 325. I remember there's 10 to the negative 3 and 1, and they'll do this, divide wrong, and they'll get 325,000. And of course, that will be one of the answers on the multiple choice. And well, that student now has got that wrong. Okay, it's really hard to get that wrong if you write out the units, because you know whatever unit goes here must immediately go down here before you fill in these numbers. So please, please, please write out your units. Now, you might have more than one set of parentheses, one unit factor involved. So let's look at something else. This is common in the medical system. Hospitals often use deciliters, but something you get from the pharmacy or from your supplier might have a volume in milliliters. So let's look at this. We're going to set it up exactly the same way. Still the patented three-step method. Okay, what is the volume in milliliters? So that is the unit I'm asked for. I'm going to write that over here. What is the unit I'm given? 125 deciliters. Now, that I've written out the units, I can always do this first step, right? And the first step is going to be whatever unit is written here, I immediately write again down here, right? So that's my deciliters. Now, it is convenient when I can make the exact exchange to the thing I want. But maybe, and let's pretend, you don't have a unit equation memorized. You don't know how many deciliters are in a milliliter, okay? And that's okay. You don't have to. The importance of this chart is that you're memorizing everything to the base unit, and that's all you need to know, right? This is saying 1 deciliter is 10 to the negative 1 liters. So that I do know, and that maybe you have memorized, right? So you might not know deciliters to milliliters, but you know deciliters to liter, right? 1 deciliter is 10 to the negative 1, that's what the deci stands for, liters. And you say, okay, well, now a deciliter unit divided by a deciliter unit cancels out, and you're left with liters. So now it's like you're starting the problem all over again with the unit liter. So what do? Well, you take this unit of liter and you say, oh, it's up here. I know it has to go down here, right? You're letting the units here sort of drive the bus, so to speak, of how you're converting these numbers. And what are you going to convert the liter to? Well, it's a good idea to see if you can convert it to the unit that is asked for. Remember, this has to go in the numerator somewhere of one of these unit factors. Now's the time. And it's the time because you know the conversion between milliliters and liters. Just like you knew 1 deciliter is 10 to the negative 1 liters, you probably also know that 1 milliliter is 10 to the negative 3 liters, right? Those two things you have memorized. And so I'm using those two things in conjunction. Now I'm looking at milliliter, a 1 goes with that, 10 to the negative 3 goes with liter. My liter will get canceled out, and I'll be left with milliliters. And now it's 125 times 10 to the negative 1 divided by, and make sure in your calculator you're doing divided by parentheses 10 to the negative 3 to get your final answer. So this times 10 to the negative 1 divided by 10 to the negative 3 should give you a number like 12,500 milliliters. Okay? 125 times 10 to the negative 1 divided by 10 to the negative 3. Okay? You can fill this out exactly the same way if maybe you don't remember 1 milliliter is 10 to the negative 3 liters. Maybe instead you remember, well, I remember the equivalent, 1,000 milliliters is 1 liter. That's fine. Whatever you remember, write it down and let the units guide you. Now it looks like 1,000 milliliters with 1 liter. Again, it doesn't matter which way you remember it, those two things were equivalent. As long as you're letting the units guide you and the number goes with the unit as it appears in the unit equation, you will be fine. I sort of usually work these out with reference to how it appears in this table that I ask students to memorize. And again, in the previous lecture, we talked about this table always being one of these prefix units, right? 1 milli and 10 to the negative 3 of the base unit. So 1 milliliter is 10 to the negative 3 liters. So for this chart, that's the way I'm working these out. Now, one complicating sort of wrinkle of these problems is you might have not one, but multiple steps. You might not have just metric to metric. You might have metric to English. Now, if everybody used metric, this wouldn't be a problem. And you wouldn't have to do these headache of a problem, right? But some countries use the English system, things like inches, pounds, quarts, instead of centimeters, grams, and milliliters. So we have to remember these conversion factors, and we need to use them in our dimensional analysis. We're still going to use the patented 3-step method, but we're just going to involve these unit factors instead. Now, while the metric-metric conversion was exact and we didn't have to worry about Sig Figs, whatever Sig Figs we started with in the problem were the Sig Figs we ended with in the metric-metric conversions, because all those relationships, all of these were exact unit equations. The problem is when we're converting between metric and English, we generally limit it to 3. So the things in this table, you'll notice are all 3 Sig Figs, but those aren't exact numbers, they're rounding, right? 946 milliliters and 1 quart? Not really. If you Google it, there's 946.353, and there's actually more digits out here. But for brevity, we just list 3. And so this we're going to limit to 3, which means that affects the precision of our measurement, and we need to take count of it for significant figures. If you're confused with significant figures, you can go back and watch some of the previous lectures on those topics. But here we're using English to metric. We have to use 3 Sig Figs. And that's generally what is done. Now, if you were using this relationship, maybe you can use 6 Sig Figs, but general in the classes that I teach, the conversion factors look like this, and we use 3 Sig Figs. So let's put all this together, right? And try in the next minute or so to solve this problem yourself. It's not as easy as it first looks, okay? You're given this conversion here, but try to set it up using the method we described and try to work out to a final answer, report it with the unit. How many meters did this running back run if he ran for 120 yards? So take some time, try to figure it out. Okay, maybe that was enough time. Maybe it's not. Don't be rushed. But for the sake of time, I'm going to go forward and start solving this, right? And I'm going to still use this, 3-step method. How many meters did this running back run? Okay, well, equals M for meters. 120 yards, that is what's given. So here's 120 yards. Okay, I know I need a unit factor in the middle. I might need more than one. I'm not really sure. Let's see how far we get. Whatever unit is given here, I'm just going to immediately write down here. I'm not worried thus far about where numbers are going. I see a unit factor that I'm given here. I don't have to memorize because it appears right here in the problem. 1.00 goes with yard. 0.914 goes with meter. The yards will cancel out because a unit divided by itself, just like a number divided by itself, cancels. Okay, and now you have to multiply across the top. 120 times 0.914 gives us a number like 109.68 meters. But that is not the right answer. Yes, that's what the calculator spits out, But remember what we just got done talking about, metric to English conversions. Pay attention to the Sig Figs. So here is 3 Sig Figs. So you might say, well, I can't report 109, right? I want to make this 3 Sig Figs. So maybe I would report 110 decimal meters. Or maybe I would report 1.10 times 10 to the 2 meters. Okay, that would be also wrong. Because if you've forgotten about Sig Figs, when you multiply, you think about the Sig Figs here, 3 and 3, multiplied by 2 Sig Figs here. This 0 is not significant. There is not a decimal point after it. It is not certain. So this really is only 2 Sig Figs. And so 2 Sig Figs times 3 Sig Figs. In multiplication, you're limited to the least number of Sig Figs of the things you're multiplying or dividing together. So we should be limited here to 2 Sig Figs. So that's not right. That's not right. That's not right. The right answer would be 1.1, only 2 Sig Figs, times 10 to the 2 meters, or 110 without a decimal here, meters. Okay, those two things would be equivalently correct. Now, another type of unit factor you might have to use, and a dimensional analysis problem you might have to solve, is one that uses compound units. And this is one that usually trips students up, so let's look at this in a little bit of detail. These compound units often appear like this: miles per hour, gallons per liters. Okay? The trick is to solve just like we have been solving, but don't write the units like this. Okay? Please write out the units like this: miles over hours. And these things are always whatever, if it's 54 miles per hour, 36 miles per hour, 25 gallons per liter, it's always per 1 in the denominator. So a lot of times, if it's 54 miles per hour, I like writing out 54 miles per 1 hour. Okay? And that is what I'm starting my sort of unit problem with. So let's look at this problem on the bottom: 105 kilometers per hour. Convert it to meters per second. You're going to do 2 different sort of dimensional analyses in one for the numerator here, kilometers. This will be 105 kilometers per 1 hour. And if you want to get this to meters per second, you have to convert kilometers to meters, and you have to convert hours to seconds. So you have to set up unit factors for each of those types of conversions. And rather than belabor the point here, I'm going to show how this is done here. 105 kilometers per hour. This is what I'm starting with. This is my first unit factor. Whatever was written here, I immediately write down here, and it goes away. I'm converting it to meters because that is, do as I say, not as I do. I'm going to put the seconds down here. I'm converting this kilometers to meters. And now I have meters in the numerator, which is good because that's what I want right here. I have seconds in the denominator right here. So I better somewhere have seconds in the denominator. That's why it comes there. Hours needs to go in the numerator here because it appears down here. And so this second unit factor is relating hours to seconds. There's 3,600 seconds in 1 hour. Hour goes into the top so that it's canceling this hours. Seconds in the bottom because it appears in the final answer in the bottom. And now you multiply across the top, divide by the bottom. You should get 29.2 meters per second. So these compound units sometimes give students problem, but I like writing it out 1 unit on top of another, and then immediately the first thing you do is use a unit factor to cancel this first unit and get it in the unit you want, and then take care of this second unit. And that one must go in the top to cancel it out. And so they'll always have this cadence of canceling units. Make sure at the end, the only units you're left with are the units ultimately you want in your final answer. Now, please, please, please write out your units. Okay? it may seem a pain in the butt to do, right? But these things really matter. It's going to matter on exams to make sure you're carefully keeping track of all the units, to make sure that you're actually putting the unit factor in the right place and getting the right answer. But it also has a lot of far-reaching consequences. And the best example of this, as sad as it is the Mars Climate Orbiter, which cost about $100 million to the United States government and NASA. And the story goes that an engineer from NASA incorrectly used English units instead of metric ones, causing the spacecraft to crash into Mars instead of orbiting the planet. And so that's $100 million right down the drain. Now, a little bit more background and detail was Lockheed Martin actually used a certain unit and its software interface. Okay, while a second system that NASA used expected the results of that software to be in metric system units or SI units. So the software actually was calculating the impulse produced by thruster firings, and it gave it in pound force seconds, pounds being an English unit. The trajectory calculation software by NASA expected it to be in Newton seconds, but it wasn't, making it off by about a factor of 4. So it turns out NASA didn't blame Lockheed Martin. While they were using their software, it's still up to NASA engineers to double check these things. And so the discrepancy between this calculated and measured position, right, made the discrepancy between the desired and the actual orbit quite different. And so the insertion altitude was way off. Some actual engineers noticed this might be a problem and reported it up the chain, but some of the higher ups at NASA, in a rush to get this thing launched, sort of buried some of those concerns, we'll say. So in any sense, there was a lot of disagreement. It got buried, and the exact thing that some of these engineers initially feared came to fruition. English versus metric, you lose $100 million with an error like this. So on that note, that wraps up this second lecture where we really talked a lot about dimensional analysis. Now, you're also going to use dimensional analysis in more complicated conversions with percentages and densities. There's also conversions that go into temperature scales. And so each of those concepts will be discussed coming up in the next lecture. So that'll do it for this one. See you next time.